Hello everybody, welcome to Psychopharmacology, Chapter 4, Part 3. Today we're talking about tolerance. So broadly speaking, tolerance is diminished response to a drug after repeated exposure. Cross-tolerance also exists. This is tolerance to one drug, diminishing the effectiveness of another. So if drugs are similar in terms of what receptors they act on or by what mechanisms they are degraded and removed, we can have cross-tolerance developing if drugs are sufficiently similar. There also exists sensitization, sometimes called reverse tolerance, which is the enhancement of drug effects after repeated exposure. So if tolerance is the decreasing response to drugs after repeated exposure, sensitization is increasing the effect of that drug with repeated exposures. It's possible to simultaneously experience both tolerance and sensitization to different effects of the same drug. So for example, with repeated use of cocaine, the euphoric response will develop tolerance, so it'll feel less good each time, whereas the motor sensitization effect will sensitize and become more severe. Okay, so there's a couple of different flavors of tolerance that I want to talk about. The first is metabolic tolerance. This is what it sounds like, an effect on the metabolism of the drug. So when you take a drug and it makes its way through your system, it has to be metabolized. So enzymes sort of inactivate it, convert it to a different form, and then they're able to excrete it. So changes in that metabolic process are what underlie metabolic. Basically, your system gets better at metabolizing a drug with repeated exposures to it. Repeated use of a drug reduces the amount of drug that is available at the target tissue because the efficiency of the metabolism becomes so much. So as I sort of mentioned, the most common form of this is the drug increasing its own rate of metabolization through a process we call enzyme induction. So basically, exposure to a drug will cause the production of an increased amount of these enzymes to increase metabolic capacity. More enzymes that do that biotransformation being present means that it's going to happen faster. We have more efficient biotransformation because we have more enzymes around that can metabolize the drug faster. So cross-tolerance can take place in terms of metabolic tolerance. So alcohol is something that I often use as an example with metabolic tolerance because the chief form of tolerance that is developed to alcohol is metabolic. And it's through this sort of enzyme induction process. So the same enzymes that metabolize alcohol also metabolize other things like some types of anti-seizure medication and some types of sedatives. So if you are a heavy alcohol user who has a high tolerance to alcohol, you will also exhibit a high tolerance to some anti-seizure medications and some sedatives, despite the fact that you've never taken them. This is because the same family of enzymes is responsible for degrading all of those drugs. So more of that enzyme being available means more efficient breakdown. Okay, the next flavor we're discussing is pharmacodynamic tolerance. These are just, broadly speaking, changes in nerve cell function that compensate for continued presence of drugs. One of the most common mechanisms we see, and the one we'll talk about the most, is receptor up and down. So if your drug is working on a specific receptor type and you're sort of bombarding it with high levels of stimulation, in an effort to sort of even things out, your cells might actually internalize some of those receptors, actually remove receptors from the synapse. That way, there are less receptors available. It sort of brings things back down to a more reasonable level of stimulation. You have all of this drug that's an agonist for that receptor, bombarding those receptors. Pulling some of those receptors back can sort of return to closer to homeostasis, the same level of stimulation, because more ligands, fewer receptors, sort of evens things out a little bit. Likewise, downregulation is sort of the opposite effect. If you have a chronic upregulation is sort of the opposite of that. If you have an antagonist on board, because there is just less signaling available, more receptors might get trafficked into the synapse to sort of, again, try to reach some sort of equilibrium. As you might expect, these compensatory changes can actually help explain to some degree withdrawal symptoms. So this sort of neuroadaptive mechanism can produce effects that are opposite to the initial drug effects. So if you have a drug that is producing extreme euphoria, like big elevations in mood because of its action on a particular receptor, you can imagine that if that receptor is being downregulated, if you stop taking that drug, you're going to have a huge drop-off in that pathway, right? It's going to be much less effective. This can create a very profound effect to the opposite of what you were experiencing while you were on the drug, producing that withdrawal state. This homeostatic shift can underlie what we call the dark side of addiction, which I'll explain in just a moment. But this compensation is not limited to just things like mood. So if we take that example again of alcohol, alcohol sort of enhances inhibitory signaling. So it sort of puts your brain into a less active, sort of slower state. There's a lot more inhibitory signaling taking place. After chronic heavy alcohol use, compensatory changes that take place in response to that can put your brain into a hyper-excitatory state. Because it's so used to being slowed down by the enhancement of inhibitory signals, when you suddenly remove the alcohol from the system, all of those compensatory changes that have put into place make it hyper-excitatory and actually prone to seizure activity. Okay, so here's what I meant by the dark side of addiction. So this figure is taken from a paper by George Koob in 2016. He is the head of the National Institute on Alcohol. The basic idea is this. We, as an organism, like homeostasis, right? We like to stay about the same. We like to stay in a comfortable zone. And let's say with something like mood, you have a homeostatic point of about where your mood should be. If you take a mood-enhancing drug, that's going to produce a temporary sort of increase in your mood. Those compensatory mechanisms we talked about, those tolerance mechanisms, could cause you to swing under as a result of that, right? So when you're in a withdrawal state, you're in a negative mood state. As a result, you might use drugs again to bring you up to a slight bump, but then you drop into an even further mood state. As things go on, your homeostatic point sort of shifts, what we come to call allostatic points. It gets lower and lower. So your new normal is now a lower mood state. In addicts, this represents a shift from drug seeking to feel good to drug seeking to feel okay, to feel how you used to feel when you were at your homeostatic point before this sort of cycle of use and withdraw, driving the resting point down lower and lower. So basically what I'm trying to get at here is this gets at the sort of negative reinforcement motivation behind drug taking, that at some point chronic users of drugs are not using them to feel good, they're using them to alleviate withdrawal symptoms and to put themselves back into a functional state rather than a high state. The last form of tolerance we are discussing today is behavioral tolerance or context-specific tolerance. This is the idea that it's tolerance that depends on a particular context. It's a tolerance effect that would not be present in a novel context. So many psychoactive drugs elicit reflexive effects, things like cortical arousal, elevated blood pressure, euphoric state, etc. And these powerful physiological states can act as unconditioned stimuli. If you think back to what you learned in an intro psych about unconditioned stimuli, it's the same thing. It's learning to associate a cue with an outcome. So with repeated pairings, cues in the environment can become associated with the unconditioned effects, arousal, elevated blood pressure, euphoria, etc., that are going to come as a result of the drug being taken. So basically, you can learn that something is coming and you can sort of your body can produce a conditioned response before that drug is even taken, in response to cues such as drug paraphernalia or a specific. So tolerance, especially this behavioral tolerance, develops when the conditioned anticipatory response is compensatory. So let me unpack that a little bit. So basically, if the environment associated with use will elicit responses opposite to the drug effect. So you can think about this as your body sort of just getting ready for what's about to happen and producing a compensatory sort of effect. And this can be a pretty basic physiological thing. So for example, certain opiates will produce a decrease in body temperature, hypothermia. So in response to being ready to administer an opiate, your body could actually produce a hyperthermic response. So as you're getting ready to use the drug, you might actually increase your body temperature in response to the expected drop in body temperature. So yeah, interestingly enough, in that instance, because opiates produce a state of hypothermia, a drop in body temperature, you can actually get an increase in body temperature and sort of an anticipatory sort of effect. This happens across multiple systems within your brain. This is in fact the reason why sometimes people taking a dose that they're very used to taking in a novel environment can experience an overdose. So if you're a chronic user and using the same amount of a drug every single time, you found a dose that works for you, but you're doing it in the same place, and you go to a new place to take that drug, because you don't have these conditioned behavioral tolerance effects, these sort of effects that are opposite to the drug effect, a drug overdose can actually be produced by a comfortable, commonly used dose, just because the setting has changed. Okay, so that's it for our discussion of tolerance. Next time, we're moving on to a more thorough discussion of some specific neurotransmitter systems and how drugs can work within those systems. See you then.